In this lecture video, we're going to be looking at the gamma distribution. Now, this is a very important family of distributions. There are several special cases of the gamma distribution that are used in inferential statistics, and we'll see them in upcoming modules. Now, the PDF, the probability density function of the general gamma distribution, is given in the middle of slide 316, and you can see that there are two parameters associated with this distribution, denoted alpha and beta, where both alpha and beta have to be positive. And in the denominator of the PDF, there is a strange-looking symbol, the uppercase Greek letter gamma, and this represents the gamma function, which we're going to look at in a fair amount of detail in the next several slides. Now, before we do that, I just want to say that when a random variable has a distribution with this PDF, then it's said to have a gamma distribution with parameters alpha and beta. And to denote that, we're going to use this abbreviated notation here, which we've seen before for different distributions. And remember, this tilde is read is distributed as. And so we would read this as the random variable x is distributed according to a gamma distribution with parameters alpha and beta. Now, we're going to be interested in trying to find the cumulative distribution function, the CDF for this distribution. We're also going to be interested in trying to find the mean, the variance and standard deviation, the skewness and the kurtosis, and also the moment generating function, which would help us find those distributional characteristics that we just mentioned. Now, to start out, we're going to take a look at this at the gamma function, which is the function in the denominator of the gamma PDF. So for alpha greater than 0, for positive alpha, define the following function, denoted this way, with an uppercase Greek letter gamma for the function symbol, and then the argument, which we're denoting by alpha, which again can take on any positive real number. And it's defined to be this integral, the integral on the positive part of the real line of x raised to the alpha minus 1 power times the exponential function evaluated at negative x. Now remember that the exponential function raised to or evaluated at a particular expression is just the real number e raised to that power. So this could also be read as the integral on the positive part of the real line of x raised to the alpha minus 1 power times e raised to the negative x power. And then we integrate that product, that function, which is a product, over the entire positive part of the real line. Now, this is a fairly complicated integral. And so the one question would be, does this integral actually exist? And it can be shown that the integral does exist and that it's finite for every positive value alpha. Now, a course in which this might be proved, that the integral exists, would be, for example, in a class like advanced calculus or real analysis, which are above, certainly beyond calculus 1, which is the prerequisite for this class. And so we're not going to get into the proof of the fact that this integral exists and it's finite. We'll just take it as given. I also want to point out that this function, the gamma function, which again is represented by or defined by this integral, is positive for all values of alpha that are greater than 0. All right, and this is fairly obvious. The integrand here over the positive part of the real line for values of x greater than 0, x raised to the alpha minus 1 is going to be positive. E to the minus x is always positive. And so that we have a product of positive functions. And so the integrand is positive, and we're evaluating it over the values of x that are positive. And so this integral will be positive for all positive values of alpha. And so we can conclude this as well. So anyway, this function gamma is called the gamma function. And it is, again, it shows up in the denominator of the PDF of the gamma distribution. Now, there's several useful results concerning the gamma function. Theorem 1 says let k be a positive integer, then the gamma function evaluated at alpha plus k is equal to alpha plus k minus 1 times the gamma function evaluated at alpha plus k minus 1. So to evaluate the gamma function at a value alpha plus k, we decrement the argument by 1. So we have alpha plus k minus 1. And then we evaluate the gamma function at that same value, alpha plus k minus 1. And then we take the product, and that will give us the gamma function evaluated at alpha plus k. Now, a corollary to that theorem, corollary 1.1, says that the gamma function evaluated at alpha plus 1 is equal to alpha times the gamma function evaluated at alpha. The second corollary to theorem 1 says that the gamma function evaluated at alpha plus k can also be written as the product of this product that I've got highlighted and the gamma function evaluated at alpha. Now, what we have here inside the parentheses is the product. That's what this notation here corresponds to, if perhaps you're not familiar with that. It's analogous to the sigma notation for representing summations. Okay, here we're taking a product and of multiple terms, and so we're using the uppercase Greek letter pi to represent that product. And so this is the product, j going from 1 to k, of the values alpha plus k minus j. So we take the product of those values and then multiply it by the gamma function evaluated at alpha, and that's going to give us the value of the gamma function evaluated at alpha plus k. Theorem 2 says that the gamma function evaluated at 1 is equal to 1. Theorem 2 says that the gamma function evaluated at 1/2 is equal to the square root of pi. And then Theorem 4 says that if n is a positive integer, then the gamma function evaluated at that positive integer n is equal to n minus 1 factorial. And because of this, the gamma function can be thought of as a generalization of the factorial function. Now let's look at some proofs of these results. This is a theory course, and so we're going to spend some time looking at proofs and doing proofs, learning how to prove things. And so let's look at a proof of Theorem 1. Now, by definition, the gamma function evaluated at alpha plus k is equal to the integral over the positive part of the real line of x raised to the alpha plus k minus 1 power times the exponential function evaluated at negative x. Now we can evaluate this integral using integration by parts. Now this is a technique that you may or may not have seen in your first calculus class. If not, let me help. I'm going to walk you through it right now, but you may want to refer to your calculus text to see the details. So what we would do is define a variable. I'm going to call it u. That is defined to be x raised to the alpha plus k minus 1. So I'm defining this quantity here in the integrand to be u, and I'm letting the differential of v, the differential of a variable v, to be equal to the exponential function evaluated at negative x. So this expression here is the differential of v. Actually, what I need to do, I need to let dv be equal to this whole thing here, the exponential function evaluated at negative x dx. You'll want to make that change in your notes. And so with those definitions, then the differential of u will be alpha plus k minus 1 times x raised to the alpha plus k minus 2 dx, the differential of x. And v would be the negative of the exponential of negative x. So given that dv is equal to this whole expression right there, e to the negative x dx, again I left the dx off, I should have had it there, then that would imply that v is equal to that expression there. And so then that gives us the components that we need to use integration by parts. And again, you may want to look that up in your calculus textbook to get the details for that. But anyway, so we have the integral that we're after, the integral over the positive part of the real line of x raised to the alpha plus k minus 1 times the exponential function evaluated at negative x is equal to this expression here, negative x raised to the alpha plus k minus 1 times the exponential function evaluated at negative x. We have to take the limit of that entire expression as x goes to infinity, and then evaluate that expression at 0 and take the difference. And then plus, so this integral that we're after is equal to, again, this quantity plus the integral over the positive part of the real line of alpha plus k minus 1 times x raised to the alpha plus k minus 2 times the exponential function evaluated at negative x dx. Now, if we take the limit of this expression here as x goes to positive infinity, we get 0. If we also evaluate this at 0, we get, at x equal to 0, we get 0. And so we have to take the difference between those two results, 0 minus 0, and that's where this comes from right there. Now, I'm going to rewrite alpha plus k minus 2 as alpha plus k minus 1 minus 1. Okay, and then, and I'll tell you why we're going to do that in just a second. And I will also point out that this quantity alpha plus k minus 1 does not depend on x, and so I can pull that out of the integral as I've done here. And now, let me explain why I rewrote alpha plus k minus 2 as alpha plus k minus 1 minus 1. And the reason I did that is because when we do that, it's perhaps easier to see that this integral is just the gamma function evaluated at alpha plus k minus 1. So we get the result that we're after, that the gamma function evaluated at alpha plus k is equal to alpha plus k minus 1 times the gamma function evaluated at alpha plus k minus 1. Now, a corollary of Theorem 1, corollary 1.1, says that the gamma function evaluated at alpha plus 1 is equal to alpha times the gamma function evaluated at alpha. Now, that follows directly from Theorem 1 if we set k equal to 1. Then we have that the gamma function evaluated at alpha plus 1 is equal to alpha plus k minus 1, so alpha plus 1 minus 1, hence alpha, times the gamma function evaluated at alpha plus 1 minus 1, or alpha. And so the result follows immediately. Now, the proof of corollary 1.2, the gamma function evaluated at alpha plus k by Theorem 1 says that that's equal to alpha plus k minus 1 times the gamma function evaluated at alpha plus k minus 1. But now, the gamma function evaluated at alpha plus k minus 1, appealing to Theorem 1 again, would be equal to alpha plus k minus 2 times the gamma function evaluated at alpha plus k minus 2. But then the gamma function evaluated at alpha plus k minus 2, again appealing to Theorem 1, would be alpha plus k minus 3 times gamma, the gamma function evaluated at alpha plus k minus 3, and so on, until we get to alpha plus k minus k times the gamma function evaluated at alpha plus k minus k. Now, obviously, the alpha plus k minus k will be alpha, and so when we collect all these terms together, we're multiplying those terms, we can write that more succinctly using our product notation as the product j going from 1 to k of alpha plus k minus j. And so that proves corollary 1.2. Okay, the theorem 2 says that the gamma function evaluated at 1 is 1, and that's very easily shown. By definition, the gamma function evaluated at 1 is the integral over the positive part of the real line of x raised to the 1 minus 1 power times the exponential function evaluated at negative x. Now, x raised to the 1 minus 1 power, in other words, x raised to the 0 power is just 1, and so we're left with the integral over the positive part of the real line of the exponential function evaluated at negative x. Now, we've actually shown in the discussion on the exponential function that this function integrates to 1 over the positive part of the real line, and so we have the result. That integration result is shown here as well, all right? But you may remember it from when we talked about the exponential distribution. So we've shown that the gamma function evaluated at 1 is equal to 1. Now, you probably noticed I skipped theorem 3. We're not going to prove theorem 3 in this course. Again, it requires some calculus above and beyond our prerequisite, which is calculus 1. And so we'll just take that result as given. Remember that what that theorem 3 says that the gamma function evaluated at 1/2 is the square root of pi. All right, so we'll just take that as given. Now, the gamma function evaluated at n, all right, now remember n is a positive integer here. We can rewrite this as the gamma function evaluated at 1 plus n minus 1. So we have a 1 and a negative 1. They cancel out, and so we would get 1 again. But it's useful to write the gamma function evaluated at n in this way, because then we can appeal to one of our previous theorems or corollaries. This would be equal to the product, j going from 1 to n minus 1 of 1 plus n minus 1 minus j times the gamma function evaluated at 1, which we just showed is equal to 1. And now we can simplify the terms in the product. We have a 1 and a minus 1, so those cancel out, and so we're left with n minus j as the terms being multiplied. And so expanded out, when j is 1, we have n minus 1. When j is 2, we have n minus 2, and so forth, up to j being equal to n minus 1. When that's the case, we have n minus 1, which is just 1. And so you see we have those terms here. We're taking the product, and so that is indeed n minus 1 factorial. So now let's proceed to look at the gamma distribution itself. And we're going to start off by looking at a special case of the gamma distribution, the gamma PDF. In particular, we're going to look at this function which for positive values of x takes on the, or is given by the expression x raised to the alpha minus 1 power times the exponential function evaluated at negative x divided by the gamma function evaluated at alpha. And for values of x that are less than or equal to 0, this function would evaluate to 0. And again, alpha has got to be a positive number. Now, clearly, this function is greater than 0 for all values of x greater than 0. We know that for when x is positive, then x raised to the alpha minus 1 will also be positive. The exponential function is always positive. And the denominator, when we talked about the gamma function, we argued that it is positive as well. And so this expression that applies when x is positive is strictly positive. And so we know that this function is positive for all values of x greater than 0. And in addition, when x is less than or equal to 0, this function is equal to 0. So for any value of x on the real line, this function is non-negative. And so That's one of the criteria that are required to be satisfied by a function that is a PDF. In addition, note that if we integrate this function f over the entire real line, it simplifies to the function over the positive part of the real line of this expression here. Now, the gamma function does not depend on the variable of integration x, so I can pull the 1 over the gamma function out front, outside of the integral, and then I'm left with the integral over the positive part of the real line of x raised to the alpha minus 1 power times the exponential function evaluated at negative x, but that's just the gamma function evaluated at alpha. And so we have 1 over the gamma function times the gamma function, each evaluated at alpha, and so that gives us 1. And so these two results imply that this function f is indeed a valid PDF. And so we're justified in calling it a PDF and using it in that way. Now, the next thing we want to do is we're going to want to investigate or be able to investigate distributional characteristics of this distribution, and also investigate distributional characteristics of the more general, the general gamma distribution. And what we're going to do to help facilitate that is see if we can derive the moment generating function first of this special case gamma distribution, and then once we have that, when we move on and start talking about the general gamma distribution, we're going to derive the moment generating function of that general gamma distribution, and we're going to utilize the result that we get here. So we're not going to actually take the derivatives of this particular moment generating function if we're able to find it, because this is just a special case gamma distribution. But we will use this moment generating function to help us find the moment generating function of the general gamma distribution. So let's see what we can do here. By definition, the moment generating function, if it exists, is given by the expectation of the exponential function raised to the, or evaluated at tx, t times x. And so this would be the integral over the entire real line of the exponential function evaluated at t times x times the PDF of the distribution of x. And so that simplifies to the integral over the positive part of the real line of e to the tx times x raised to the alpha minus 1 power times e to the negative x all over the gamma function evaluated at alpha. Now, notice that I've got e raised to the tx power and e raised to the negative x power. So I have like bases, and when I'm multiplying those quantities with like bases, the exponents add, and so that's where I get t times x minus x as the argument of the exponential function in this line. Now I can rewrite tx minus x as minus x, negative x, times 1 minus t, right? If we distribute the negative x across the difference here, we get minus x plus t times x, or x times t, and so that's what we had there. So this is perfectly legitimate to do. And the reason we want to do this is because we're going to do the integration by substitution, where we're going to define a new variable of integration. We're going to call it y. We're going to let y be equal to this part of that exponent, x times 1 minus t. And so when we do that, the differential of y is equal to 1 minus x dt, and therefore the differential of x dx, which shows up right there, is 1 over 1 minus t dy. And so by substitution, that integral becomes the integral over the positive part of the real line of y over 1 minus t raised to the alpha minus 1 power times the exponential function evaluated at negative y over the gamma function evaluated at alpha times 1 over 1 minus t dy. Now, the 1 over 1 minus t does not, well, let me first note that we have 1 over 1 minus t showing up in two places, here at the end, and also over here. There's a y times a 1 over 1 minus t raised to the alpha minus 1 power. So the expression 1 over 1 minus t does not depend on the variable of integration y, and so we can pull that out front. We have 1 of the 1 over 1 minus t's here, and we would have 1 over 1 minus t raised to the alpha minus 1 power, and therefore when multiplied together, we would have 1 over 1 minus t raised to the alpha power. Then that's multiplied against the integral over the positive part of the real line of y raised to the alpha minus 1 power times the exponential function evaluated at negative y, all over the gamma function evaluated at alpha. And we see that that is just the gamma function evaluated at, this is the gamma PDF, which we have shown is equal to 1. And so we're integrating the gamma PDF over its sample space, and so that integral is going to be 1. And so we're left here with the expression 1 minus t raised to the negative alpha power. Now, this expression exists for all values of t minus 1. If we look at this expression for it, we see that if t were equal to 1, then the denominator would be 0, and therefore this expression would not exist. But it does exist for all values of t that are strictly less than 0, and therefore it also exists for all t in some interval about 0, and we could just, for convenience, pick the interval from -1 up to +1, the open interval, right? So we're using parentheses here, and so it's an open interval, does not include the endpoints. Now, because this expectation exists for all t in an interval around 0, the moment generating function of the distribution exists, and it's given by this expression, by this expectation, 1 minus t raised to the negative alpha power. So this is the moment generating function for the distribution of x where the random variable x has this particular special case gamma distribution. Now we're going to look at the general gamma distribution. We're going to extend and generalize the PDF that we have been looking at up to this point. And so we're going to, again, let x be a random variable, a continuous random variable. It has this PDF that we've been using, that we've been looking at. Again, this is that special case gamma PDF that we've been looking at. And since we're calling the PDF lowercase f, let's just denote the CDF of this distribution by cap f. Now, we're going to define a new random variable, which we're going to call y, and it's going to be equal to beta times the random variable x, where beta is a fixed positive number. Now, the sample space of x, the values that x can take on, are the positive real numbers, right? The values on the open interval from 0 to infinity. And when we multiply x by a positive fixed constant beta, that gives us y. The set of possible values that y can take on are also the set of positive real numbers. So the sample space of y is the same as the sample space of x, which is the set of all positive real numbers. Now, what we're wanting to do here is we want to find the distribution of y. We want to find the CDF and the PDF, and we're going to use an approach that we used previously when we were looking at the exponential distribution, when we looked at the normal distribution. In each of those two situations, we first looked at a special case of the PDF for those distributions that was fairly easy to manipulate and work with mathematically because it didn't have too many parameters. All right, and then we generalized those PDFs when we looked at the general exponential distribution and the general normal distribution. And that's what we're doing here. So we've defined a new random variable, y, in terms of the random variable that we've been looking at up to this point. And now we're going to find first we're going to find the CDF of this random variable. let's denote the CDF of this random variable by capital G. And then once we have that, then we'll be able to find the PDF by differentiating the CDF. And by the way, this technique for finding the PDF of a random variable by first finding its CDF, it's called, it's a general principle or general approach called the CDF technique. And it's a very helpful way of finding the distribution of functions of random variables. So again, we're denoting the CDF of y by capital G. Given that the sample space of y is the set of positive real numbers, if we evaluate the CDF of y at a value of y that is less than or equal to 0, then we know that that CDF has to evaluate to 0, because the CDF, remember, it's a probability accumulator, and if we evaluate it at any value of y that is less than the lower boundary of the sample space, then we've not accumulated any probability, so it therefore must be equal to 0. Now, for values of y that are positive, for values of little y that are in the sample space of the random variable y, then the CDF evaluated at such a positive value, little y, by definition is equal to the probability that the random variable y is less than or equal to the argument being fed to the CDF, little y. Now, y is equal to beta x, and so I can replace y in this probability statement by beta times x. And then further, I can divide both sides of this inequality by beta to get a probability and have x alone in this event. And since beta is a positive number, when we divide both sides by beta, the direction of the inequality stays the same. And so the CDF of the random variable y, evaluated at a positive value of little y, is equal to the probability that the random variable x is less than or equal to this value of y divided by beta. Now, we recognize this as just being the CDF of x, which is denoted by cap f, evaluated at y over beta. And so we have an expression for, we've expressed the CDF of y in terms of the CDF of x. Now that we've gone that far with the, coming up with an expression for the CDF of y, now we can take the derivative of that CDF to get the PDF. And so let's denote the PDF of y by lowercase g. Then for values of y that are not in the sample space, we know that the PDF must evaluate to 0. For values of little y in the sample space, in other words, for positive values of y, the PDF of y evaluated at that value of little y is obtained by differentiating the CDF with respect to y. All right, and because the CDF is equal to the CDF of x evaluated at y over beta, all we have to do is take the derivative of this CDF. Now, using the chain rule, that is equal to cap f prime, the derivative of cap f, evaluated at y over beta, times the derivative with respect to y of this function of y, right? And so that derivative is taken there. And clearly the derivative of y over beta with respect to y is just 1 over beta. And so I've got that out here in front. And then the derivative of the CDF of x, and so the derivative of cap f is just the little f, the PDF of the random variable x, and it's evaluated at y over beta. Now this is helpful because we already know the PDF of x, so all we have to do is evaluate that PDF of x at the argument y over beta. And so we do that, we have 1 over beta up front, and then we have y over beta evaluated at alpha minus 1 times the exponential function evaluated at negative y over beta, all over the gamma function evaluated at alpha. Now we have a 1 over beta up front, And then here we have a 1 over, there's a y times a 1 over beta, and we raise both of those to alpha minus 1. And so we can combine the 1 over beta here with the 1 over beta that's implicit in here, and we end up with 1 over beta to the alpha power. And so that's where this comes from in the denominator for this PDF. We have in the denominator, we have the gamma function evaluated at alpha times beta raised to the alpha power. And then once we pull that 1 over beta out of this piece, what we're left with is y raised to the alpha minus 1. And then we have the exponential function evaluated at negative y over beta. And so when we put those two pieces together, we get the fully specified expression for the PDF of y. For values of y that are positive, the expression for the PDF of y, this general gamma distribution, is y raised to the alpha minus 1 power times the exponential function evaluated at negative y over beta, all over the gamma function evaluated at alpha times beta raised to the alpha power. The CDF of this of the distribution of y is equal to 0 if y is less than or equal to 0, and for values of y that are greater than 0, the CDF is given by this integral expression here. Now, we're not going to be able to come up with a nice closed form formula for this, not integral. The best we're going to be able to do is to approximate it, and there are some, in some cases, there may be books that have tables for this integral, for this CDF. Many calculators, well, I say many calculators, calculators like the TI-84 don't have every possible gamma distribution, but they do have a particular special case, which we'll be, again, talking about in a subsequent lecture. But software programs like SAS, R, Minitab, and so forth, statistical programs, as well as programs, I'm sure, like MATLAB and things like that, are going to have routines that give approximations to the general gamma CDF. So we're not going to be able to come up with a formula for this, but if we happen to need values of this CDF, then we can use SAS or something like that. Now what we're going to do is derive the moment generating function of the distribution of y, the general gamma distribution. And so we're going to denote the moment generating function of the distribution of y by cap m sub y. And by definition, this is equal to the expected value of e raised to the t times y power. Now again, y is equal to beta times x, and so I can replace y by beta x in this expectation. And then by the associativity and commutativity of multiplication, I can rewrite this as beta t times x. So we have the expectation of the exponential function evaluated at beta t times x. Now the reason that we would rewrite it this way is because it makes it easier to see that this is actually the moment generating function of x evaluated at beta t. So what we have here is we've expressed the moment generating function of y, which we don't know, in terms of the moment generating function of x, which we do know, and this happens to be evaluated at beta times t. Now, the moment generating function of x was equal to 1 minus t. Well, let me back up. The moment generating function of x evaluated at t was 1 minus t raised to the negative alpha power. Since we're evaluating this moment generating function of x not at t but at beta t, this expression turns out to be 1 minus beta t raised to the negative alpha power. And so this is the expression for the moment generating function of the general gamma distribution. And so let's summarize the results for this general gamma distribution with parameters alpha and beta. So I'm going to switch up the notation just a little bit. I hope this is not confusing, but I'm just going to, let's let X now have a general gamma alpha beta distribution. Previously, X was our special case gamma, but now we're just going to let X have a general gamma distribution with parameters alpha and beta. Then the PDF of X is given by this expression here, okay? Alpha raised to the x minus 1 power times the exponential function evaluated at negative x over beta, all over the gamma function evaluated at alpha times beta raised to the alpha power, as long as x is positive. If x is less than or equal to 0, then this PDF evaluates to 0. The CDF is going to be 0 if we evaluate it at any value of x less than or equal to 0, and it's going to be given by this integral expression which we just talked about a few moments ago. And then the moment generating function of the general gamma alpha beta distribution is given by 1 minus beta t raised to the negative alpha power. Now, there's more than we could learn about this distribution. For example, now that we have the moment generating function, we could use the moment generating function to generate the raw moments, the first 4 raw moments. From those first 4 raw moments, we could find the variance. We could find the third and fourth central moments. And from those, along with the variance, we could find the skewness coefficient and the kurtosis. I'm not going to do that in this particular lecture video because you're going to be doing this in an upcoming lab assignment. So I don't want to take the fun away from you. I want you to have the ability to do this on your own. So anyway, but you see here how what we've done to come up with the PDF and the moment generating function, 2 very important functions for this general gamma alpha beta distribution, by first starting off with a special case gamma distribution and then generalizing that particular special case gamma random variable by multiplying by a scale factor beta, which was positive. So that's all I'm going to say in this lecture video about the gamma distribution, other than the fact to remind you that, again, this is a very, very important distribution, very important distribution for continuous random variables. One of the reasons is because there are several special cases of this distribution that are used in inferential statistics. And so with having said that, we'll end this particular lecture, and we'll get into sampling distributions in the next lecture video.